Thank you. It's a pleasure to be here in the Dennis Sciama Auditorium, and reminds me what a wonderful person Dennis was, and I benefited from many conversations with him on opposite sides of the anthropic principle discussions, but it was still a lot of fun. So I'm going to talk about dark matter, of course, and the subtitle is The Decade of the WIMP, because I feel we are halfway through the decade that will finally either lead to the discovery of dark matter as a weakly interacting massive particle or put to rest the idea. I'm required as a cosmologist to show this slide at the beginning of every talk, and I also think it's important every time you give a talk or teach a class to try to describe to the audience why they should care about what you're going to talk about. And the answer to me is that most of the mass of the universe is in the form of dark matter, so it's something that we should know about. And this pie chart, which is the present abundance of various components to the mass energy density, is illustrative of several things. One is that radiation, which was once dominant in the early universe, is a small fraction of what's in the universe now. The other thing it tells us is that chemistry is not important. The chemical elements, by which as a physicist I think of elements other than hydrogen and helium, is a much smaller fraction of what's in the universe than even neutrinos. Stars that astronomers have studied for thousands of years is less than 1%. Most of the mass in the universe, most of the mass is in a hot gas of hydrogen and helium that's most easily seen in clusters of galaxies. But 95% of the mass and energy in the universe is invisible to us. It's dark. We have no idea, well, we have too many ideas of the identity of the dark matter and dark energy, but 95% of the universe is not understood. And today I will talk about the fraction of the universe that we describe as dark matter, 25% of the present mass and energy in the universe, and I'll mostly follow the idea that it is in the form of a weakly interacting massive particle. A curious number comes up, and that's the ratio of 6 to 1, which is the ratio of the dark matter mass density to the mass in normal baryonic material. There seems to be about 6 times more dark matter in the universe than visible matter. Why 6 to 1 in this cosmic recipe? That seems to be a number we should be able to predict, 6 to 1. It involves a couple of things. One is the answer to the question, what is the origin of the normal matter, the baryon density of the universe? The baryon density is determined by the baryon asymmetry, the fact that there are more baryons than antibaryons in the universe, and that's conveniently expressed in terms of a dimensionless ratio of the baryon asymmetry to the number density of photons, and that number is about 10 to the minus 9. This, there's some process of a yet unknown origin responsible for this number. One possibility for dark matter is that it is something known as asymmetric dark matter, that the same unknown mechanism that generates the baryon asymmetry generates the asymmetry in dark matter. So is the ratio 6 to 1 because the dark matter particle has a mass of 6 times the mass, say, of a proton. For most dark matter scenarios, this ratio of 6 to 1 is input, not output. Another question that eventually we want to answer is why is the neutrino contribution 0.17%? It's sort of an annoying number. It's not 0. It's just large enough that in precision calculations you have to include it, but not really large enough to really change anything. It's just an annoyance. That's what nature does. Okay, so what are the goals of the study of dark matter, both for particle physics and for astrophysics? Well, I think from the particle physics community, we want to understand the nature of dark matter. and how it is embedded within a deeper theoretical framework. If dark matter is a particle, we want to know more than just its mass, spin, and couplings. We want to know how it fits into a model or theory. We don't think that dark matter just sits out there unconnected with everything else. It's part of a larger model or theory. We want to know why dark matter exists, and we want to understand its contribution to the mass budget, why this 6-to-1 ratio. Justin did a good job of explaining what astrophysics can tell us. We want to understand the role of dark matter in the evolution of the universe and structure formation. Questions like, is the dark matter completely cold? Is there only one dark matter component? I will make the implicit assumption that the dark matter consists of one new particle. So most of the mass is simple, consisting of one particle. This small fraction of the universe, the normal matter, is quite varied. So what right do we have, what expectation should we have that the dark matter sector is so simple? Finally, the question is, does dark matter have interactions that affect structure formation? And we're going a long way to answering that. All right, so dark matters are missing pieces in understanding the structure of the universe. We arrived at the idea that dark matter is a new elementary particle. Wasn't the first thing that people thought of, but people thought of perhaps simpler things. One thing that was mentioned by Justin is that either Einstein or Newton didn't have the last word, that their general relativity is not the final theory describing large-scale interactions. For instance, Tevis, tensor, vector, scalar theories of gravity. Or there's even something wilder, in my opinion, that goes by the name of MOND, modified Newtonian dynamics. For instance, force is not equal to mass times acceleration, much to the dismay of high school physics teachers. But I found evidence for modified Newtonian dynamics from an advertisement for a Swiss watch. Modified Newtonian dynamics, right there, by a precision Swiss instrument. Another possibility of dark matter that's been explored over the years is that it is in the form of some astrophysical objects that are large and do not emit light. One possibility is that it is in my favorite type of planets. You know, there are gas planets and ice planets. Rocky planets, actually, are my favorite type of planet. And maybe the galaxy is just full of chunks of big rocks that do not emit light. Or it could be in the US, in the politically correct world in the US, we don't refer to dwarf stars anymore. We call them mass challenge stars. They are also light challenged. Or black holes would not emit light. These are known as massive compact halo objects, and the result of microlensing experiments in the late 90s sort of ruled out the idea of massive compact halo objects being the dark matter.
And you could say rules of color.
Sorry? Yeah. Careful, careful. So most of us are driven to the idea that the dark matter is in an unknown, new type, unknown particle species. So why an unknown particle species? Don't we have a sufficient number of elementary particles that are known to make up the dark matter? We have quarks, leptons, anti-quarks, anti-leptons, force carriers, and now the Higgs. Well, what do we know about dark matter? The dark particle must be stable. Must be stable, so if we get rid of all the unstable particles, well, that culls the herd a bit. The dark matter particle, it must be massive, so we can get rid of the massless force carriers. And it must be sufficiently massive, and it looks like the neutrinos that we know of are not sufficiently massive to be the dark matter. And finally, if the dark matter is a new particle species, it must interact weakly, so we can get rid of the quarks and the leptons and come to the conclusion that the dark particle must be beyond the standard model of particle physics, a BSM particle. There's a lot of different types of dark matter that have been considered. There are particles that are thermal relics of the Big Bang, or the decay products of a thermal relic, or oscillation products of a thermal relic. These particles were all in local thermodynamic equilibrium in the early universe. And this includes a large number of types of particles, sub-electron volt mass neutrinos. Neutrinos are weakly interacting massive particles. WIMPs exist. Neutrinos exist. They're not the WIMPs we want for the dark matter, but they do exist. Stereoneutrinos, gravitini, the lightest supersymmetric particles, the lightest Kaluza-Klein particles, and as Justin described, they go as hot dark matter, warm dark matter, or cold dark matter. Then there are the possibility of non-thermal relics, particles that were not produced because they were in thermal equilibrium. Bose-Einstein condensates, axions, axion mini-clusters. Could be that it's not an elementary particle per se, but rather some coherent scalar state, a soliton, Q balls, B balls, etc. Or they were never in equilibrium. They were produced just by the expansion of the universe. That would be supermassive WIMPzillas. These are non-thermal relics. So about 40 years of hard work by theorists have limited the mass of the dark matter to be a mere 81 orders of magnitude in mass, between 10 to the minus 56 grams for a Bose-Einstein condensate to 10 to the plus 25 grams for axion mini-clusters. So we've done the observers and experimentalists a favor by narrowing the range of masses. We've also been so good as to narrow the interaction strength between only gravitational interactions and strongly interacting particles. So there you go. Look for a particle with interactions between strong interactions and gravitational interactions in this mass range, and let me know when you found it. I will concentrate on cold thermal relics. And the assumptions are there was a new species of particle, a dark matter species, that was in thermal equilibrium at temperatures larger than the mass, in thermal equilibrium with standard model particles. The equilibrium abundance of the dark matter is determined only by its ratio of the mass to the temperature. In other words, there is no chemical potential or asymmetry between matter and antimatter. And as the universe expanded and cooled, the dark matter particle froze out of equilibrium. And the present abundance and mass density of the dark matter particle is determined by its freeze-out. Now, the freeze-out is an interplay between the dark matter standard model interaction strength, which presumably is in the realm of particle physics, and the expansion rate of the universe, which is determined by the Friedmann equations from Einstein's theory of gravity. So it's an interplay between particle physics and gravity. I refer to these as cold thermal relics because they are a relic of the Big Bang, and I think it's the Oxford English Dictionary of relic is an object of particular veneration, and many of us venerate the idea of a cold thermal relic. So these are the words. There's a picture that goes along with the words. That's a graph of the relative abundance of a particle species which has no chemical potential in thermal equilibrium. At temperatures larger than the mass, it's about as abundant as any other particle. And if it would remain in equilibrium, as the temperature drops below the mass, its abundance would be decreased by the Boltzmann factor, e to the minus m over t. But the particle freezes out of equilibrium, and where it freezes out of equilibrium determines its present contribution to the mass density. But the more strongly interacting the particle, the longer it stays in equilibrium, and the lower would be its abundance today. So the more strongly interacting particles stay in equilibrium longer, Boltzmann suppress longer, and will have a smaller contribution to the energy density. This is not a new idea. A very influential paper, at least influential to me, was about 39 years ago last May, a paper that was written by Ben Lee and Steven Weinberg. And I dug out of my files. For the younger people in the audience, this was called a preprint. They used to be typed up and mailed to people. This is in the prehistoric era before archives. And Fermilab preprints were nice yellow colored before everything had to be on white paper. So this was a paper by Lee and Weinberg. And in this paper, they have essentially the same figure that I showed here with different interaction strength and masses, the particles starting in equilibrium. For some reason, they show about 11 orders of magnitude of a constant. So there's a couple of things interesting about this very influential paper. The model was a fourth generation GeV mass heavy neutrino with an annihilation cross-section given by essentially a 4 Fermi interaction form. It was motivated by an incorrect Fermilab experimental result, the high Y anomaly. Anybody remember the high Y anomaly? No? I remember it. The model was based on effective field theory. Again, Weinberg didn't use anything fancy like the Weinberg-Salam model. It was Fermi effective field theory. This model was shortly excluded by direct detection experiments and by neutrino counting at LEP. But it still was a very influential paper, and many of the equations and concepts that we use still today were contained in this paper from 39 years ago. This is an example. In the paper is something that we refer to as a Boltzmann equation that tracks the evolution of the number density of a particle species with time. It has an expansion term. It has a term due to annihilation of the particle and a term due to the creation of the particle from the thermal bath. And the thing that enters is the thermal average of the cross-section, of the annihilation cross-section. And if you go through the arithmetic, the calculations, you find that the present contribution to the mass density is the value we think it is today, 0.11, 0.12, and it's inversely proportional to the annihilation cross-section. Again, as the annihilation cross-section is larger, the particle stays in equilibrium longer and freezes out with a lower density. And the number that comes here is about 10 to the minus 36 centimeters squared for the predicted cross-section. Now, actually, the calculation is not quite so clean. There's velocity dependence in the cross-section, possibility of resonances, co-annihilation, log dependence on the mass, decay production spin dependence, asymmetry, et cetera. But that's the basic idea. Now, we can convert 10 to the minus 36 centimeters squared as alpha squared over 150 GeV squared, and 150 GeV is about the weak scale. Doing this calculation, before you do it, you don't know what sort of mass scale will enter. It could be anything from the Planck scale to micro, nano electron volts. What enters is the weak scale, or what comes out is the weak scale. This is known by some people as the WIMP miracle. I don't know who referred to it as the WIMP miracle, but it was a terrible thing to do. What is a miracle? One definition is it is an extraordinary event manifesting divine intervention in human affairs. We don't think that's appropriate for dark matter. Probably a better description of what a miracle is in Wikipedia. It's a word that's often used to give an impression of great and unusual value in a trivial context. Nevertheless, the WIMP hypothesis, that is a weakly interacting particle, predicts a dark matter mass range, something around 150 GeV, and the interaction strength between dark matter and standard model particles. Does not predict the 6-to-1 ratio. So the WIMP hypothesis relates the dark matter mass and dark matter interactions to a known scale, the weak scale. That's very attractive. So WIMPs and cold dark matter. Cold dark matter is cold, has a negligible velocity during structure formation. It's dark, we can't see them in any wavelength, and it's matter, it's massive. WIMPs are a cold thermal relic. It's part of the thermal bath in the early universe. Its present abundance is determined by freeze-out. It froze out when non-relativistic, or at least semi-relativistic. Now, cold dark matter need not be a WIMP. Axions are an example of cold dark matter, but they're not a thermal relic. Asymmetric relics would be cold dark matter, but it's not a thermal relic either. It's in the sense that its abundance is not determined by freeze-out. And weakly interacting massive particles as dark matter need not be a cold thermal relic. An example of that is WIMPzillas or Gutzillas, which is the latest incarnation of them. Now, how do we think about this weakly interacting massive particle? I'd like you to sort of differentiate this idea between social particles and maverick particles. So a social WIMP is, dark matter here, is friended by many light mass particles. It pals around by new unwimpy particles. For instance, in supersymmetry, the dark matter has other particles, supersymmetric particles, that have a mass comparable to its mass, leptons, quarks, charginos, gluinos. And the dark matter particle is part of a larger theoretical framework. Generally, these are top-down models where you start with a model that is constructed for some reason, like supersymmetry, top-down, and you end up with dark matter. Generally, these models are ultraviolet complete. And the way to find the WIMP in these models is not by finding the WIMP, but finding its more strongly interacting friends. And an example of this, of course, is supersymmetry. The other limit is that the WIMP is a maverick particle, and it interacts with normal matter, or we see it, through the intermediation of a much more massive particle. And so it's not friended by any new light mass particles. Its unwimpy pals are beyond reach. So if you have an accelerator just able to produce a black sheep, you're not going to be able to produce an elephant. So there's some intermediate state that's much more massive than the dark matter particle. Doesn't really have a theory framework in the maverick. It's sort of a don't ask, don't tell. Just use effective field theory. Generally, it's not ultraviolet complete, and you would detect the WIMP through looking for something that's not seen, like missing energy or missing momentum. And an example of such an effective field theory and the discovery of a weakly interacting massive particle goes back to the Fermi theory of weak interactions. So let me just mention these two limits, and I'll use supersymmetry as an example because the evidence for supersymmetry has never been stronger. It was developed in the late 70s, in the early 70s, and in this model, every known particle has a superpartner. The superpartners are massive. The lightest superpartner should be stable. And in many realizations of supersymmetry, the lightest superpartner is weakly interacting, so the lightest supersymmetric particle is a candidate WIMP. Now, there are many realizations within supersymmetry of dark matter. The dark matter could be a gravitino, a neutrino, an axino, but the one that's the most studied is that it's a neutralino, which is a linear combination of SUSY partners of the photon, the Z, and the Higgs bosons. The mass and linear combination depend upon about 100 SUSY parameters. So what's done is to reduce to a manageable number of parameters by looking in some models which have the more initials they have describing the model, I think the more unlikely it is to be true. So the minimal supersymmetric standard model didn't quite work, so you add additional letters, and then when these don't work, there'll be more and more letters added to describe the model. There are many processes and diagrams contributing to the annihilation of the WIMPs into many channels, W, Zs, Higgs, fermions, etc. One thing to note that I'll turn to later is the annihilation into fermion pairs is proportional to the fermion mass. And there is no two-body final state with a photon at lowest order in these models. The LHC and other experiments have pushed the SUSY scale high, usually to too large, resulting usually in too large of a value of omega h squared, unless there is some chicanery to increase the annihilation cross-section. And the chicanery is in three main areas. One is the area of focus point SUSY, it's known, where the neutralino has a large Higgsino component, or either resonant annihilation, where in the early universe, in the non-relativistic limit, the neutralino annihilation goes through an intermediate particle which has a mass that's just a little bit larger than twice the mass of the neutralino. Or it co-annihilates with another particle, say the tau, the supersymmetric tau, which has a mass that's, again, just a little bit larger than the mass of the neutralino. And this has to be tuned, finely tuned. If this is not correct, if this is not, or let me say the present abundance, mass density of the neutralino depends sensitively on this relationship or that relationship. So in that case, in that regard, it is finely tuned. For the lightest neutralino, it's a linear combination of SUSY partners. As I said, choose a model framework to reduce from about 100 SUSY parameters. You have to require a consistent low energy model with a neutralino as a dark matter candidate that satisfies all experimental constraints. The low energy annihilation cross-section, which determines the present abundance, depends upon the neutralino composition, mass, and coupling, and possibly other masses, and all of these depend upon 100 SUSY parameters. Generally, the annihilation is some constant plus another constant that depends upon the velocity squared. I'm sorry, that's difficult to read. So there's a velocity independent annihilation part plus a velocity suppressed part. So the SUSY dark matter phenomenology is very interesting and very rich. And the SUSY dark matter relationship on Facebook, it's complicated. And whether you like this or don't like it depends upon your point of view. For maverick effective field theory, the WIMP is the only state accessible to experiments. The other states that will enter in the non-relativistic WIMP annihilations have a mass much larger than the mass of the WIMP. Many theories have common low energy behavior when mediating particles are heavy compared to energies involved. Effective field theory is not as desirable as an ultraviolet complete theory. I would buy a UV complete theory if I knew of one. You can miss relations between quantities, and you can't describe the high energy behavior, possibly high energy relevant to the LHC. One example of this type of interaction would be if the dark matter is fermionic and couples to quarks. And in general, the present dark matter density will be proportional to the mass of the mass of the WIMP squared divided by some high energy scale to the 4th power. So this would determine the present density of the dark matter. So if this combination is tuned to give the dark matter density in the observed range, then it's a good WIMP candidate. One thing we do know, if the dark matter is a WIMP, it must interact with standard model particles. The relic abundance is determined by the annihilation of WIMPs into standard model particles. This would also be the process by which I will discuss indirect detection of WIMPs. And this actually is a cartoon Feynman diagram. So there's a cartoon Feynman. And cartoon Feynman would say we can do some crossing symmetries and change directions of arrows. And it would suggest that WIMPs should scatter with standard model particles. And we can take advantage of that looking for WIMPs through direct detection. And cartoon Feynman would say you can also move the arrows around and reverse the directions. And you can have standard model particles producing WIMPs. And this would be used for collider production of WIMPs. So let's look at maverick WIMPs and assume that the interactions are that the WIMP is a fermion and the lowest dimension effective field theory that would describe the interactions, say, with quarks. And to determine the dark matter abundance, omega h squared will determine for a given mass of the WIMP what the interaction strength will be, what the lambda that's appearing in the effective field theory would be. So you input omega h squared, and for a given mass of the WIMP, you determine lambda. And some operators have velocity squared suppressed annihilation, and some are unsuppressed at low energy annihilation. If the WIMP is self-conjugate, for instance, if it's a Majorana particle, then these operators do not exist for Majorana particles, and there are only 6 possibilities. So that determines the present abundance. How can we test the idea that the dark matter is a WIMP? One way is through direct detection, which was first proposed 31 years ago. There's nothing very new in what I'll say today. And it was pointed out that, in fact, there is an interaction between dark matter and standard model particles that we may be able to observe. So in order for direct detection to work, there are some things we have to know. We have to know the local WIMP phase space density, usually assumed to be 0.4 GeV per cubic centimeter. But there are issues having to do with subclumps and streams, et cetera, what the WIMP dark matter density is. And we also have to know the velocity distribution. It's usually assumed that it's Maxwellian with a velocity distribution of 220 kilometers per second. Let me skip over this, which is some indication from numerical simulations that these assumptions might be good. So we also have to know whether the interaction with nucleons is spin-dependent or spin-independent. For instance, if it's an axial vector interaction, then the cross-section will depend upon the spin of the target nucleus. Finally, we have to know whether there's the same coupling to protons and neutrons. There could be destructive interference if the WIMP couples with different signs to protons and neutrons. So the picture here is sort of straightforward. A WIMP comes in, bumps into a nucleus, and causes a nuclear recoil. The WIMP is non-relativistic, and it gives a recoil energy to the nucleus. And the rate for this per recoil energy depends upon things like the mass of the nucleus, the local density of the WIMP, the mass of the WIMP, and some integral over the phase space density of the WIMP. Generally, the recoil energies are a few to a few dozen keV, and astrophysics enters in determining the local mass density of the WIMP, the phase space density of the WIMP. Particle physics enters in determining the mass of the WIMP and the cross sections. And the experimental handles you have are the detector mass, which nuclear target you use, what is the mass of the nucleus and the spin of the nucleus, the threshold energy, which depends upon the reduced mass, the minimum velocity, and the mass of the nucleus, and the cross section. For direct detection experiments, different techniques are used, either ionization, phonons, or scintillation light, and most experiments use some combination of a couple of these. So you have to turn the nuclear recoil in a target to a signal. Now, looking for WIMPs is not new. The first paper that reported limits on WIMPs was 29 years ago this month, and it reported a cross-section of smaller than about 10 to the minus 40 centimeters squared. Today, there are about 20 experiments underground where my colleagues dress up in funny costumes and go underground or wear helmets in case a WIMP hits them in the head. And they do experiments, very difficult experiments underground, looking for direct detection. This is a diagram which shows some experimental limits on the WIMP nucleon cross-section deduced by various experiments as a function of the mass of the WIMP, and these are some of the experiments that I've listed. The green area here is the total excluded region in the cross-section mass plane. And it's really quite amazing the limits that have been reached for the WIMP nucleon cross-section. Up here is a picobarn, a femtobarn, an attobarn, and now we're sort of approaching the zeptobarn limit. Experiments in the future will go down to a yoctobarn, something I don't use every day, a yocto. What is 10 to the minus 51 centimeters squared? If anyone knows, please let me know. I can't find it in any handbook. I don't think it has a name. There is a floor here that would be where we would have events from neutrino scattering, either neutrinos from the sun up here or the background of neutrinos, the diffuse astrophysical neutrino background. So we're pushing down about 2 orders of magnitude every 5 years, and eventually we will hit the neutrino floor. This is for direct detection, and this is an example, just in looking at a maverick theory, of what would be predicted by a maverick theory for direct detection. So the limits now rule out masses larger than about 300 GeV, and in the future we'll rule out or discover particles in the range up to about a TeV. If the cross-section is spin independent, this would be an example if it's a vector interaction, and we've already ruled out this maverick model. If the interaction is spin dependent, the limits are not quite so good, and this is an example of a spin dependent model, and it rules it out up to about 50 or 60 GeV, and in the future we'll rule it out close to a TeV. Now for supersymmetric WIMPs and the direct detection relationship, again, it is complicated. It's not so easy to deduce what the answers are. This is one example of the type of things that are done. This is The sweet spot, according to this paper, for supersymmetry, largely driven by the anomaly in the muon dipole moment. Well, I won't say any. Let me go on. So at present, for direct detection, maverick WIMPs for a given mass choose a lambda and determines the relic abundance. For vector couplings, it's excluded in the range between 10 GeV and 2 TeV. For scalar couplings, is excluded in a narrower range. Axial and tensor couplings are spin-dependent. There are weak or no limits. And pseudo-scalar couplings are velocity suppressed. Again, there are no limits. For supersymmetric WIMPs, make your choice of 100 or so SUSY parameters. Any limits are very model-dependent. Direct detection limits are constraining. But the LHC is pushing the SUSY scale high, pushing to higher mass WIMPs. The future of this, experiments are being supersized to the neutrino floor, going down in this direction, and new techniques are being developed to push the excluded region to lower mass, lower annihilation, lower recoil energy. So let me turn to indirect detection and collider experiments in the last minute and a half. Again, indirect detection is not a new idea. It goes back to about 38 years ago. And the idea behind this is that today, in the galactic center, dwarf spheroidal dark matter clumps in the sun, WIMPs are accumulating, having accreted there. They annihilate, producing a high-energy jet full of quarks, leptons, and bosons, which we would detect as positrons, electrons, neutrinos, or perhaps antiprotons. So for the indirect detection, we want to know what the differential flux is, and we have to know the mass profile of dark matter, how the energy density scales with radius from the detection from the object we're looking for. What do we look for? We can look for charged particles. They're easy to see. There are astronomical backgrounds and they're bent by magnetic fields. We can look for continuum photons and neutrinos. The photons are easier to detect, but they're astronomical backgrounds, and neutrinos are hard to detect, and they're usually not the dominant annihilation channel. Or we could look for monoenergetic photon lines. Where should we look for indirect detection? Where should we point our telescopes? Toward the galactic center. We know where the galactic center is. It should be the largest signal, but it's also the largest background. Perhaps there are nearby subclumps of dark matter. This would be clean. There would be no baryons in them, but we don't know where to look, and the signal is down by about a factor of 1,000. Dwarf spheroidal galaxies that Justin spoke about is another possibility. We know where they are, at least where about 20 of them are around us. It's clean, there are very few baryons, and the signal's down by about another factor of 1,000. There are a dozen or so observational platforms looking for a signal of indirect detection, balloons flown from the South Pole, experiments at the South Pole, satellites, Namibia, or even Arizona. And what we've learned, we can combine what is seen or not seen in direct and indirect detection experiments and put together some idea of the type of operators that would give a direct signal, a spin-independent direct signal, plus an indirect signal, a spin-dependent direct signal, plus an indirect signal, or various combinations. So combining indirect detection and direct detection or non-detection gives us an example. Let me finally say a word about collider experiments. My friends who look for new particles saying looking for new particles is like looking for a needle in a haystack, but if you're looking for a WIMP, it's looking for an invisible needle in a haystack. Looking for maverick WIMPs at the LHC, what you're looking for is missing energy. You can have, say, QQ bar producing a WIMP pair. The final state is nothing. But if the initial state quark, for instance, radiates a jet, the final state that you would see would be an energetic jet of particles with unbalanced momentum. You're looking for monojets. Monojets are nature's garbage can. At colliders, every new theory produces monojets. You can also produce monophotons or mono-Zs. The standard model background is extremely well modeled and understood. The neutrino background can be removed with judicious cuts. And the question has to do with the validity of effective field theory. For SUSY WIMPs at the LHC, the gluino, squarks, et cetera, would be discovered first. Any analysis is very model independent. As we speak, LHC is chewing away at the allowed region. You can do the supersymmetric version of wiggling out. You can squiggle out of any argument, any limits, but it's getting harder. Don't throw in the tauolino yet. Stay tuned for the final results from the 13 GeV run, and eventually we'll see the WIMPs in missing energy signals. And again, SUSY WIMPs, looking for them directly, it's complicated. Collider searches for the future. LHC has started running at 13 TeV. Eventually, it will accumulate a tremendous amount of data. If dark matter is a SUSY relic, some indication of SUSY will be discovered at the LHC. Search strategies are well developed. As dark matter is a maverick particle, the only hope is missing energy searches, most effective for low mass, but there's no guarantee effective field theory is valid at LHC energies. What if dark matter is not a WIMP? There are many other possibilities: axions, asymmetric dark matter, sterile neutrinos, axinos, self-interacting dark matter, inelastic dark matter, Q-balls, quark nuggets, hidden sector dark matter, WIMP-zillers. The list goes on. What is the future of dark matter? We are in the 8th decade of dark matter, tracing back to the 1930s. The 2010s is the decade of the WIMP. LHC is running. We have direct detection experiments that will either discover or close out the possibility of direct detection of dark matter. Indirect detection, telescopes and observations in observatories and satellites are at the requisite sensitivity to discover WIMPs by indirect detection. And I think we have to run to ground the WIMP, the cold thermal relic hypotheses. Indirect, direct LHC confusion is not an issue. 5 years ago, I had this terrible fear that there'd be signals from colliders, signals from direct detection, and signals from indirect detection, and we wouldn't figure out how to combine these signals. That hasn't turned out to be true. WIMPs may be more complicated than discussed. There are leptophilic, leptophobic, flavorful, self-interacting, dynamical, inelastic. It's really a theorist's playground. My predictions: we will know the answer before a century of dark matter. Dark matter discovery will be unanticipated. It will be none of the above. Dark matter will be multi-component. It will be a more complicated dark sector than we imagine, and it will be part of a dark sector. So stay tuned. This is the decade of the WIMP. By the end of this decade, we will know the answer whether WIMPs are dark matter or they are excluded. And I've been saying this for 30 years, so I'm sticking with it. Thank you.